In the previous lectures on curvilinear coordinates, we have discussed so many facts regarding these curvilinear coordinates. Now we are going to discuss the three important operations, particularly of vector calculus. And those operations are gradient of a scalar function, divergence of a vector function, and curl of a vector function. But in this lecture we will see only the gradient of a scalar function, particularly in orthogonal curvilinear coordinate system. And for this, let us consider a scalar function, or you can say a scalar field, which will be actually a function of the general curvilinear coordinates, which we have denoted by the symbol u1, u2 and u3. So to define the gradient in orthogonal curvilinear coordinate system, let us consider a scalar function. So let phi of u1, u2, comma u3 be a scalar point function, be a scalar point function. And you can see I have considered that this scalar function phi is actually a function of the curvilinear coordinates u1, u2 and u3. So you can say that this scalar function is given in terms of the orthogonal curvilinear coordinates. So you can say given in terms of orthogonal curvilinear coordinates. And what are those curvilinear coordinates? You know, these are u1, u2 and u3. Actually, you know, the gradient operation is denoted by a particular symbol, that is actually the del symbol. And when you will operate that del operator on any scalar function, you get the gradient of that very scalar function. So grad phi, it means gradient of phi. This is actually denoted by this symbol del phi. And actually this del operator is a vector differential operator. And whenever it is operated on a scalar function, we get a vector quantity. So del phi, this will be actually a vector. Gradient operation is defined for a scalar function, but gradient of a scalar function is not a scalar, but it is a vector. So if it is a vector, you can express this vector in terms of their rectangular components and also in terms of the unit vectors which you have defined earlier in the orthogonal curvilinear coordinates. So let this vector quantity del phi is equal to f1 e1 hat plus f2 e2 hat plus f3 e3 hat. You have seen in orthogonal curvilinear coordinate system, we denote a vector by this manner. Here you know e1 hat, e2 hat and e3 hat, these are actually the orthogonal unit vectors. And f1, f2 and f3 are actually the components of this vector del phi, that is grad phi, in the direction of the unit vector e1 hat, e2 hat and e3 hat. So if we want to know the value of this del phi in orthogonal curvilinear coordinate system, then we must have to evaluate the value of these components f1, f2 and f3. So how we will determine the value of f1, f2 and f3, we have to see. And for this, you know the transformation equation that the position vector r of any point relative to an arbitrary origin is expressed as a function of the curvilinear coordinates u1, u2 and u3. And what is that transformation equation? You have already studied these things in the previous lecture. So now you can say that our transformation equation is r equal to r of u1, comma u2, comma u3. Here r, this is position vector of the point P, where P is located in a space anywhere, and u1, u2, u3 are actually the curvilinear coordinates of that very point P. We have seen this transformation equation earlier. When we have defined this curvilinear coordinate system, then you have seen this transformation equation. Now, if we want to find the elementary change in this r, that is if you want to find the value of dr, so you can see, since r is not a function of only one variable, but it is a function of three independent variables, and those are u1, u2 and u3. So to find this dr, we must follow the rules of partial differentiation, and you know it. We have studied these things several times during your course in mathematical physics. So what will be this dr? You can say, first of all, we will differentiate this r partially with respect to u1, and after that with respect to u2, and after that with respect to u3. And so dr is written as del r by del u1 du1, plus you can say what will be the second term. You can easily say this will be del r by del u2 du2, and plus del r by del u3 du3. Now you have seen in the previous lecture that this del r by del u1, del r by del u2 and del r by del u3 are equal to what? You can remember the results of the previous lecture. You have seen that this del r by del u1 is actually a vector which is called basis vector, and it is along the tangent to the u1 curve, and this is equal to h1 e1 hat if our coordinate system is orthogonal. Then del r by del u1, you have seen this is h1 e1 hat. So this will be h1 e1 hat du1. And similarly, this del r by del u2, this is h2 e2 hat. All these things you have seen in the earlier lecture. And plus del r by del u3, this is what? You can say this is h3 e3 hat and du3. You know, in here this h1, h2 and h3 are known as scale factors. You have seen earlier in these things in your course on curvilinear coordinate system. So you can express this dr in this manner. Now, first of all, we will find what will be the scalar product of del phi and this dr. So you can easily see when you will take the scalar product of del phi and dr, let us say this is equation 2, then as you know, our coordinate system is orthogonal, and in an orthogonal coordinate system, you know, EP hat dot EQ hat is equal to Kronecker delta PQ, and this is equal to 1 if P is equal to Q, and this is equal to 0 if P is not equal to Q. So you know E1 hat dot E1 hat, that will be 1. Similarly, E2 hat dot E2 hat will be 1. E3 hat dot E3 hat will be 1. But when you will take E1 hat dot E2 hat, or E1 hat dot E3 hat, or E2 hat dot E1 hat, E3 hat dot E2 hat, it means when the subscript 1, 2 and 3 will be different, then you can see this scalar product will be 0. So in this condition, what will be the scalar product of del phi and dr? You can easily say. So you can write it. Therefore, del phi dot dr. You can easily see that according to this result of the orthogonal curvilinear coordinate system, that this will be equal to simply h1 f1 du1 plus h2 f2 du2 plus h3 f3 du3. You can easily see it. See here, when you will take the scalar product of f1 e1 hat with this h1 e1 hat du1, then e1 hat dot e1 hat will be 1, and all other terms when you will take the scalar product with f1 e1 hat, that will be 0. So your result is like this. But we know this del phi dot dr is equal to what? This is simply d phi. This is the differential change in phi. So you can say, since del phi dot dr is equal to d phi, so this d phi is equal to h1 f1 du1 plus h2 f2 du2 plus h3 f3 du3. h3 f3 du3. You can see del phi dot dr, this is simply equal to d phi. And let us say this is your equation number 3. Now, you can see that this function phi is actually a function of u1, u2 and u3. So you can also find this d phi in terms of u1, u2 and u3. So as phi is equal to phi of u1, u2, u3. So from here you can easily find what will be d phi. We will again follow the rule of partial differentiation, and you can see this will be del phi by del u1 du1 plus del phi by del u2 du2 and plus del phi by del u3 du3 and say this is equation 4. Now see equation number 3 and equation number 4. You can see the LHS of both of these equations are same, so definitely their RHS will be also equal. So if we will equate these two equations, that is 3 and 4, what will be our result? You can easily see. So from 3 and 4, you can see that this h1 f1 du1 plus h2 f2 H2 F2 du2 plus H3 F3 du3. This will be equal to what? That will be equal to del phi by del u1, del phi by del u1 du1 plus you can say del phi by del u2 du2 and plus del phi by del u3 du3. Now you know u1, u2 and u3, these are independent variables. So similarly you can say that this elementary change in u1, u2, u3, that is du1, du2 and du3, these are also independent from one another. So such equation is actually known as in mathematics as an identity. So if du1, du2 and du3 are independent from one another, then this identity will be valid only when the coefficient or multiple of du1, du2 and du3 in LHS and in RHS will be same. Only then this equation will be valid. Reason is what? Reason is that du1, du2, du3, all these are independent from one another. So for the validity of this identity, the coefficient of du1 in LHS must be equal to the coefficient of du1 in RHS. Similarly, the coefficient of du2 and du3 in LHS must be equal to the coefficient of du2 and du3 in RHS. So if you will equate the coefficient of du1, du2 and du3, what will be our result? You can easily see. So you can say equating the coefficients of du1, du2 and du3, we get what we will get. You can see. In fact, in LHS you can see the coefficient of du1 is h1f1 and that of in RHS it is del phi by del u1. So you can write h1f1 is equal to del phi by del u1, and since h1 f1 is equal to del phi by del u1, so you can see this f1 will be what? f1 is 1 over h1 del phi by del u1. And similarly, you can write the expression for f2 and f3 in the light of this result. So I am just writing directly what will be f2 and f3 after equating the coefficient of du2 and du3 in LHS and RHS. So you can say similarly you can say what will be f2? f2 will be 1 over h2. You have only to change the subscript 1 to 2. So your result will be 1 over h2 del phi by del u2. And f3, what will be this? You can say this will be 1 over h3 del phi by del u3. So you can see we have evaluated the values of f1, f2 and f3, which is nothing. These are actually the components of gradient of phi. You can see here the equation number 1, these F1, F2 and F3 are components of del phi, that is gradient of phi. So as we have evaluated F1, F2 and F3, so after substituting all these values of F1, F2 and F3 in our first equation, we can get the value of gradient of phi in the orthogonal curvilinear coordinate system. So you can say from equation 1, what is del phi? I am just repeating equation 1 here for your convenience. You have seen that del phi have been defined in this manner: F1 E1 hat plus F2 E2 hat plus F3 E3 hat. Now substitute the values of F1, F2 and F3 which we have just evaluated. You can see after substituting these values we will get F1 is 1 over H1 del phi by del U1, and here is E1 hat plus what is F2, you can see here this is 1 over H2 del phi by del U2 E2 hat, and plus 1 over H3 del phi by del U3 E3 hat. And actually this is the definition, you can say, of gradient of a scalar function in the orthogonal curvilinear coordinate system. So you must remember this result, because this is just a defining equation, that this is just the definition of gradient of a scalar function phi in orthogonal curvilinear coordinate system. So you must remember it. And from this equation you can easily define what will be the expression for the gradient operator, that is the del operator. So general expression for this gradient operator or del operator in terms of orthogonal curvilinear coordinates you can easily see. So the expression for del operator in orthogonal curvilinear coordinates system, curvilinear coordinates, you can say, you can see easily here is phi, here is also phi, here is also phi. So if you will remove phi in RHS, then the remaining operator is simply your del operator. So you can see, or for your convenience I am just writing it here, that this del phi can be written as 1 over H1, or let us say E1 hat over H1 del U1 plus E2 hat over H2 del U2 plus E3 hat over H3 del U3 phi, and here is also phi. So you can compare that this del operator in the orthogonal curvilinear coordinates will be simply what? This will be E1 hat over H1 del U1 plus E2 hat over H2 del U2 plus E3 hat over H3 del U3. So this is the general expression for the gradient operator, that is del operator, in orthogonal curvilinear coordinates. Actually, when we will see the particular orthogonal curvilinear coordinate system, like Cartesian coordinate system, spherical polar coordinate system, and cylindrical coordinate system, then we will have actually to find the values of these scale factors h1, h2 and h3. Actually, these scale factors are different in different orthogonal curvilinear coordinate system. So when we will discuss the particular orthogonal coordinate system, then you will see what are values of h1, h2 and h3 in different orthogonal curvilinear coordinate system. That will be the particular coordinate orthogonal coordinate system. But here we have defined this del operator in fact in general orthogonal curvilinear coordinate system. So this is all about the gradient of a scalar function in orthogonal curvilinear coordinate system. Actually, in the forthcoming lecture, we will see the divergence and curl operator in orthogonal curvilinear coordinate system, and after finishing those things, we will see some of the important problems to clarify this concept.